Okay, so here's our experimental setup. We've got the hose on the left set up to put out a high velocity airstream, and the hose on the right set up to put out a low velocity airstream. And when I turn on the switch, the golf balls will demonstrate the difference in the streams. This is the low airspeed blower setup. It's a blower connected to a variac set down to 50 volts, and it feeds the hose on the right. This is the high-speed blower setup. It's two blowers connected together with a T-coupling that feeds into the hose on the left. Okay, so now we have some low-velocity air coming out of this hose, about approximately 5 meters per second. Out of this hose, air is coming out at about 10 meters per second. This hose is going to be directed along the baffle and directly along the surface, and this hose is oriented like you see. Let's see what happens. If a student were to logically apply the faster air equals low pressure theory, they would have to expect the dish to move to the left in this case, because there was faster moving air on that side of the dish. But instead we saw the dish move to the right. Here's another trial, except for this time we're going to turn on only the jet on the right with the low velocity air to set up sort of a control to see what happens if we have nothing coming out of the high velocity jet. Took a second to build up to speed. Okay, now I'm going to turn on the low velocity air on the curved side and the high velocity air on the straight side. Again, we see the dish move toward the curved side, which had the lower velocity airstream. Okay, now we have a straight-sided object, which is a little small tool drawer on the rollers. Again, we have slow-moving air coming out here and fast-moving air coming out here, and a little baffle to make sure the air doesn't catch the edge of the drawer. Let's see what happens. No movement that I could see. Now let's turn off the slow-moving air, so all we have is fast-moving air coming out here and no air coming out of that hose. See what happens. If students were to logically apply the theory of fast-moving air equals lower pressure, they would expect the drawer would move to the left, which would be the faster moving air side in either of these two trials, but what looks like it doesn't move at all. Okay, so we just saw two demonstrations in which we expected to see a lower pressure where we had faster moving air, but we didn't observe what we would expect. But now let's use a manometer to do an experiment to see if we can figure out what might have gone wrong. Okay, now I'm going to direct a high-speed stream of air over this manometer tube with a flat plate on top and see what the pressure is, and then I'm going to direct it over this curved tube. Let's see what happens. Looks like Okay, so it looks like the air passing over the flat plate was in fact at atmospheric pressure. The air passing over the curved plate was a little bit less than atmospheric pressure. So it looks like this is indicating that a free stream of air, if it's not curving, even though it's a high velocity, does not have a lower pressure than the surrounding still air, at least to the resolution of this manometer. and that would explain some of the surprising results in the previous demonstrations. Okay, now that we've learned that result from the manometer, let's try another experiment that addresses the idea that the low pressure area is created when streamlines are crowded together and therefore the air speeds up. So we're going to try an experiment that has no streamline crowding and see what happens. Okay, now we have a surface that is flat and then curves around to a 90 degrees so that there won't be any crowding of streamlines. The air is going to come out of this nozzle tangent to the surface, and there will be no air coming out of the other nozzle. Let's see what happens. Here's another trial with a close-up view. So now things are getting even more interesting. We established with the manometer that the airstream coming out of the hose is at atmospheric pressure. In this case, we can't really apply a Bernoulli argument that says the air speeds up because the streamlines are getting crowded together, because we don't have any streamlines getting crowded together, really. So we might have to think of another explanation for why there is a force on the elbow-shaped object. What we would really like to do is to come up with a simple and elegant explanation to teach to beginning physics students that they can easily apply to a variety of phenomena such as these to make correct predictions.